All right, the big thing for any type of kinetics unit is going to be to determine the rate law. And the rate law is a specific mathematical equation that relates the reaction rate and the concentration of its reactions. And again, don't forget that rates are measured in frequency of a successful collision. Now, here's the really important part to remember. Rate laws are super, super specific. So they differ for every different type of chemical reaction. They differ with different concentrations in pure substances. They differ if you add a catalyst. They differ if you heat it up or change it even a half of a degree. Not to mention that the forward rate law is definitely going to be different than the reverse of the rate law, the reverse reaction rate law. Okay, so I don't want you getting too bent out of shape about these because you have to look at the individual situation to figure out the specific rate law. All right, rate laws we are going to assume are going to be for our forward reactions. That's all that we're going to cover because that is going to basically talk about when you have initial concentrations of your reactants. So for this scenario, we have 2H2 plus 2NO making N2 and 2H2O, and this is specifically going to occur at 125 degrees Celsius. Okay, it depends on the temperature. The rate will change if I put this at like 126 Celsius or if I put it at um, 27 Celsius, anything like that, it's going to change. But in general, what you are doing for your rate law is R stands for rate. It's going to have a rate constant, which we'll talk about in a little bit, that's going to account for the temperature. And then it's going to take the concentration of your reactions to sometimes their coefficient, but it's more proper to say order. And the order isn't necessarily the same thing as being raised to their coefficients. It will only be that way if it's a one-step process, okay? But the exponents in the rate law will not always equal, okay? Not always equal the stoichiometric coefficients. All right, you have to look at the data, okay? So this is completely data driven, and this is where using labs to reinforce this really shows this. Okay, but you can see sometimes that the exponents are equal to the stoichiometric coefficients if we talk about the rate determining step. Okay, and the RDS we'll talk about in upcoming videos. All right, so the rate law of a forward reaction will have an order, and that's talking about whether or not you will see an effect of the concentration on the rate. All right, so the big numbers are having a 0th order, a first, a second, or a third order reaction. All right, in a 0th order, there is no effect on the initial rate of the reaction to that reactant. Okay, first order means that the initial rate will double when the amount of the reactant is doubled. So that means it has, one complete um, similar effect to it. A second order reaction would quadruple if you doubled the reactant. And in a third order reaction, it would increase eightfold or if you increase the concentration of the reactant by 2. All right, so let's take a look at some data for this. All right, and this is what a typical rate law problem would look like. So you are figuring out the rate law of the forward reaction for our example, like so. All right, and remember this is specific at 125 degrees Celsius. And they give you data. This is why you always look at data. So they've run 3 experiments, 1, 2, and 3. They give you the initial concentration of hydrogen, they give you the initial concentration of nitrogen monoxide, and they give you the initial rate, okay, in molar per second. Okay, so first they give you a 0.005 molar concentration of H2 and of NO, and then you see this is the rate. In the second experiment, what do we do here? We go from 0.005 to 0.01, so this guy gets doubled. okay, whereas this guy is constant and stays the same. So you're looking at what was the effect on the rate, okay? Did it speed up? Did it slow down? What happened? In the third reaction, okay, these two guys stayed the same and these two guys doubled. So what happens to the rate there? All right, so we're going to use that data to determine the overall rate law of the reaction at this temperature. Then we're going to go over the overall order of the reaction. Then we're going to plug in the units for K and figure out what the rate would be if we had this much and this much of our two products, or our two reactants, excuse me, at 125 degrees Celsius. All right, so let's do exactly that. So the rate law of the forward reaction. So like I said, we're going to compare experiment 1 and 2 first. So in an experiment 1 and 2, okay, the concentration of H2 is what changes. Okay, this doubles. This stays the same. Okay, so if the concentration of H2 increases by 2, what happens to our rates? All right, so what happens here? The rate goes up by, and if you can't do this in your head, you can definitely plug it into your calculator. Okay, 5.00 times 10 to the negative fifth divided by 1.25 times 10 to the negative fifth is going to be 4. So if the concentration of the hydrogen increases and the rate goes up by 4, what is 2 to the x power? Okay, what is x going to be? X is going to be 2. So this is going to be to the second order. All right, so hang on to that. Now let's see what happens when we change our concentrations in experiment 2 and 3. Okay, these concentrations for hydrogen are going to stay constant, but the concentrations for nitrogen monoxide are going to double. And what happens to these two? All right, so the concentration of our NO is going to increase by 2. What happens to our rate? Our rate is going to it's going to increase 1.00 times 10 to the negative fourth over 5.00 times 10 to the negative fifth. That's going to be 2. So I'm going to call this 2 to the y is equal to 2. Well, what does y equal? Y equals 1. So this means it is first order. So what is my overall rate law going to be? Rate is equal to the constant, K, times, oops, that's supposed to say H2, the concentration of H2 to the second order, and the concentration of NO to the first order. So that is my rate law. And I want you to notice a couple of things. All right, this 2 is visible up here, but this 1 is not the same thing as that one up there. So you cannot use the stoichiometric coefficients here. All right, sometimes you can. It works out with the data. Sometimes you cannot. In this one, you cannot. All right, so just to review for you, okay, if you increase the concentration of H2, okay, by 2, the rate goes up by 4. So 2 to the x equals 4, so x equals 2. And over here, the concentration of NO is going to double, and the rate is also going to double. So that means it is first order with respect to NO. So this is our rate law, and then you see the reaction is second order with respect to H2, and the reaction is first order with respect to NO. All right, so what is the overall order of the reaction? All right, well, what is the overall order? If it's second here and it's first here, 2 plus 1 gives you 3. And it is third order. Okay, that's as simple as all you have to do. You literally are taking the first order and the second order and adding them together. This little sign right here, okay, means therefore. Okay, so therefore it is third order overall. All right, so what are our units of K? Okay, this is where you have to just simply plug back in. So get your calculator if you don't already have it, and you are going to plug into our rate law right here. R equals K to the concentration of H2 squared to the concentration of NO to the first. All right, so choose an experiment. I'm going to choose experiment 1 and I'm going to plug in. Okay, so the initial rate over here is 1.25 times 10 to the negative fifth, and this is molar per seconds, equal to K, which I'm trying to solve for. And then I have my concentration of H2, 0.005 molar squared, and my concentration of NO is 0.0020 molar to the first. And what I like to do first is deal with my units. Okay, so molar per second, and then we have molar squared times molar. So what we're going to do is we're going to cancel out one of our molars, and then we have molar squared that we need to divide and put under here. So K is equal to 1 over molar squared seconds. And then we are going to square this value, multiply it by this value, and then do this number divided by that. And what you should get is the number 250. Okay? 250 molar squared per second. All right, so if you need to see that again, all right, you can choose any of the experiments. You will get the exact same value regardless of the experiments. Okay, you plug everything in, you get 250, 1 per molar squared, molar squared per second, and that is specifically at 125. All right, so then for the last part of this problem, what it's asking you to do is to calculate what the rate would be if you ended up having this specific concentration, okay, 0.012 molar H2 and 0.006 molar at 125. You literally plug it right back in to your original rate law problem, R equals K H2 squared over NO to the first. Okay, and you're trying to figure out what R is now. So you plug in your 250, 1 over molar squared per seconds. You're going to plug in your 0.012 molar. We're going to square that, and the concentration of 0.0060 molar to the first power. Okay, got to know your algebra, got to know your rules here. Okay, so we have molar squared. We have molar squared up top, and then we have 1 molar. So molar squared and molar squared are going to cancel out. We're going to be left with units of molar per seconds. And we're going to do 250 times 0.012 squared, and then we have our 0.06, and we get 2.16 times 10 to the negative fourth, which we would round to 2.2 times 10 to the negative fourth because we have 2 sig figs over here and 2 sig figs over there. So we're going to leave it like that. All right, so lots of plugging into the same types of equations here. Into that same rate law. So that's what you need to figure out first with the data, and then you can figure out your units for K, and then you can plug in to get your R for a specific scenario. And make sure that your units work out and you get your molar per second.